What if I told you that one of the most powerful tools chemists have for building complex molecules, I'm talking the stuff in medicines and materials, it all comes down to the special powers of a single hydrogen atom? Well, today, that's exactly what we're going to explore. We're diving into the aldol condensation, a reaction that lets simple little molecules build themselves into amazing structures, all because of one very important player. So this is one of the biggest questions in chemistry, right? How do you actually build big, complicated things from small, simple pieces? If you want to make a new drug, you've got to have a reliable way to snap carbon atoms together to build up that molecular skeleton. And the aldol reaction? It's one of the most classic, most elegant answers to that exact problem. Okay, so to get this, first we have to meet the star of the show. Look here, see that carbon double bonded to an oxygen? That whole C double bond O thing is called a carbonyl group. Now the carbon atom right next door to it, that's what we call the alpha carbon. And that means the hydrogens attached to that carbon are, you guessed it, the alpha hydrogens. See them here in magenta? Those are the ones we're going to be focusing on. All right, so why all the fuss? I mean, a molecule can have a ton of hydrogens. What's so special about these alpha hydrogens? Why are they the key to this entire reaction? What is their secret? Okay, here it is. Their secret superpower is that they're surprisingly acidic. Now, this happens for two big reasons. First, that oxygen in the carbonyl is super greedy for electrons. It's constantly pulling them towards itself, which tugs them away from the alpha carbon and weakens the bond to its hydrogen. So that hydrogen is already kind of halfway out the door. But the second part, this is the real magic. Once a base comes along and plucks that hydrogen off, the negative charge that gets left behind isn't just stuck on the carbon. It can spread out, sharing itself with the oxygen. We call this resonance. And by spreading that charge out, the whole thing becomes way more stable. That stability is why the hydrogen is so willing to leave in the first place. So now what? What can we do with this acidic hydrogen? Well, if you put it in with a base, that alpha hydrogen gets ripped off, and suddenly the aldehyde transforms into an attacker. Chemists call it a nucleophile. This new, aggressive molecule immediately looks for a target, and it finds the carbon of a second aldehyde molecule. It attacks, and bam! A brand new carbon-carbon bond is formed, the one you see here in orange. This is the heart of it all. We just stitched two small molecules together to make a bigger one. And this thing we just made, it gets a special name, an aldol. And I love this name because it's not random at all. It's a perfect description. If you look at the molecule, it has an aldehyde part on one end, and it has an alcohol part in the middle. You just smash the two words together, and you get aldol. See? It's beautifully logical. But wait, the story's not over yet. That aldol product we just made, it's often just a temporary stop. If you add a little bit of heat, something else happens. The molecule gets rid of a water molecule. The OH from the alcohol and a nearby hydrogen just pop off. This is the condensation part of the name because a water molecule is literally condensing out of the reaction. What you're left with is a new double bond, which makes the final product even more stable. Now, you might be wondering, is this just an aldehyde thing? And the answer is no. This awesome reaction isn't that exclusive. If a ketone has those crucial alpha hydrogens, it can play the exact same game. You can see it right here with propanone. Two of them combine, kick out a water molecule, and follow the same pattern. The only real difference is that the intermediate is called a ketol, for ketone and alcohol. But the overall process is the same. The principle is what matters, and it's identical. Okay, time to crank up the difficulty. Instead of just reacting one molecule with itself, what if we mix two different aldehydes together? Say ethanol and propanol. Well, things get messy really fast. See, since both of them have alpha hydrogens, either one can be the attacker and either one can be the target. The result? You don't get one nice, clean product. You get a chaotic mixture of four different things. Let's try and make sense of this mess. Two of those four products are actually pretty straightforward. They're just the self-reaction products. So an ethanol molecule can just find another ethanol molecule and react with it, like we saw at the beginning. And a propanol molecule can do the same thing with another propanol. So that's product one and product two. Easy enough, right? The other two products, though, are the cross-aldol products. This is where things get mixed up. This is what happens when an ethanol molecule attacks a propanol molecule. And then there's the other possibility, where a propanol attacks an ethanol. Each one gives a totally different product. And now you can see why this can be a real headache for chemists. You end up with a flask full of four different compounds that are probably a nightmare to separate.
So, is this whole crossed reaction useless? Not at all, because chemists found a really clever trick to get it under control. What if you use one reactant that has 0 alpha hydrogens? Take a look at benzaldehyde here. It has nowhere for a base to attack. It can't become the nucleophile. It's forced to only be the target. So when you mix it with a molecule that does have alpha hydrogens, you basically force the reaction to go down one specific path, leading to just one major product. It is such an elegant solution to a messy problem.
So let's just zoom out for a second. We've gone on this whole journey, and it all started with a simple idea. One specific hydrogen is unusually acidic. That one tiny chemical fact is the key. It unlocks the door to self-assembly, letting molecules build bigger versions of themselves. And it unlocks the door to controlled, complex cross-assembly, letting chemists pick and choose different building blocks. It just goes to show how a simple rule at the microscopic level can lead to this incredibly powerful way to build our world. It really makes you think, doesn't it? If this entire essential chemical reaction was just sitting there, waiting for us to understand the property of a single kind of hydrogen, what other amazing chemical secrets are out there? What other incredible tools are just hiding in plain sight, waiting for us to look a little closer?